Hello, I wanted to give a brief little lecture on capacitors and how to deal with multiple capacitors in a circuit. This is a little bit tricky sometimes for students to work through, so I wanted to just give you a couple examples to just make sure that you know how to do the homework questions involving multiple capacitors in a circuit. So I'm going to bring up my whiteboard. Okay. So the first kind of circuit that we can have, so by the way, um, you might be wondering, like, why do I have to have multiple capacitors in a circuit to begin with? Like, what is the deal with this? So the reason being is that usually capacitors are manufactured in a way where they're standard values of capacitance. You can't just go out and buy any old random like number for capacitance. They only come in standard values. So there might be a situation where you're trying to create a circuit with a certain amount of capacitance, like you want to have a certain amount of energy here, but you can't go out and just buy that particular size capacitor. So what you have to do is build a circuit that involves multiple capacitors to get that capacitance that you need. So that's why you may have a circuit with multiple capacitors in it so that you can get this final, what they call equivalent capacitance. So let's think about that in a little bit more detail. So let's suppose I have my battery, and this is the circuit symbol for a battery, positive side of the battery, negative side of the battery. And I connect it to this capacitor like this. And capacitor, the symbol for capacitor in the circuit is two lines that are equal length. And then let's suppose I put another capacitor in this circuit. And I connect it in a way like this. So if this is a 9-volt battery, this is the positive terminal, 9 volts over here. This is the negative terminal, that's like at 0 volts. And these are two different capacitors. And they're connected in a configuration that looks like this. We call this kind of configuration a parallel configuration. It looks nice and pretty and neat and clean when I draw it like this, but if it was in a real like circuit, like if you were plugging things together in a real lab, it would basically look like here's my battery, here's the positive terminal, and I could have one capacitor like this connected, and I could have another capacitor like this. This is the same configuration as this. It's just that we draw them in the textbook very nice and neat, and it looks like this. But basically, you could take this junction right here and just stick it right on the positive end of the battery. You could take this junction right here and stick it on the negative end of the battery, and you get something that looks like this. Both of these are parallel configurations. And what you should note here is that if I look at the positive terminal of the battery and I just track it, right? This is a wire, it has very little, we're going to assume that all the connecting wires have very little resistance. We're not losing any potential energy here. Okay, so if this is 9 volts right here, everywhere along this wire is 9 volts of basically potential or potential energy if you think about it. Right? And once these things become fully charged up, they'll have positive charge on this side, depending on how much they can hold, and negative charge on the other, right? So if this is the positive side of the battery, the positive terminal, this side of the capacitor is going to be positively charged. And it will be at 9 volts because it's connected directly to the 9-volt terminal, the positive terminal. And again, I can track the wire And on the other capacitor, it is also connected directly, doesn't look like it, but it's actually connected directly to the 9 volts as well. There's nothing else in the middle here removing any energy, right? So if this is 9 volts, as long as I can track it and there's nothing else in between here, this is 9 volts. And again, I could do the same thing on the negative terminal of the battery. I track it, blah, 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 blah. This is 0 volts. 0 volts. Excuse me. So this is called a parallel connection because both of these capacitors are basically connected to the terminals of the battery with nothing else in between. They both have the same potential drop across them, and it's the same potential as the battery. And so if I wanted to replace, so maybe I was making a circuit and I was trying to get a circuit with a certain capacitance, and I had to put these 2 capacitors in there to make that capacitance. What is that capacitance? If I combine these into one equivalent capacitor, what would the capacitance of that thing be? Well, these do not they have the same voltage drop across them, right? These 2 capacitors have the same voltage, but they don't necessarily have, if this is capacitor 1, right, and this is capacitor 2, they don't necessarily have the same charge on them. They're different capacitance. They're going to have different amounts of stored charge. So this is going to have Q1 and Q2. If I replace these 2 capacitors with one equivalent capacitor, the total charge on that equivalent capacitor, we'll call it Q. The total charge on that thing would be Q1 plus Q2. Now I'm going to use the relationship that capacitance is equal to the charge stored divided by the voltage. And I'm going to solve this for charge. So this is going to be charge stored is equal to the capacitance of the capacitor multiplied by the voltage across it. And so this Q, capital Q of the equivalent capacitor, if I replace these with one capacitor, its total charge would be the equivalent capacitance of that thing multiplied by the voltage that it's connected to, which in this case would be 9 volts. That has to be equal to the charges on capacitor 1 and capacitor 2. The charge on capacitor 1 is capacitance 1 multiplied by the voltage that it's connected to, which is 9 volts, which is the same voltage that everything is going to be connected to here. So I'm not making a difference between this voltage and this voltage because it's the same. They're all connected in parallel. And charge Q2 is equal to the capacitance 2 multiplied by the voltage that it's connected to, which is the same as everything else in this circuit because they're all in parallel. Notice that because all of these voltages are the same, I can cancel them out everywhere. And so the equivalent capacitance of this circuit is the capacitance of the first one plus the capacitance of the second one. It becomes very easy. In parallel, you just add them. You just add them together. So if this was a 2 microfarad capacitor and this was a 3 microfarad capacitor, the equivalent capacitance of that circuit would have been 5 microfarads. It would be acting the same way if I just replaced those 2 with one capacitor with 5 microfarads. So that's how we deal with capacitors in parallel, but there's another configuration that we need to deal with which is in series, is what we call series. So in that case, here's my battery. And in series, the capacitors are right after the other. Let's call this my 9-volt battery again. I like to stick with 9 volts for some reason. Positive end of the terminal is 9 volts, negative terminal is 0 volts. And here's my capacitors C1 and C2. Now in this case, in the parallel case, the voltages across each of the capacitors was the same. In the series case, right, and we call this a series configuration, they're right after the other. In the series case, what is the same here is now the charge. And let's think about why. So we're going to have 9 volts, right? There's going to be a positive charge. As these things charge up, there's going to be a positive buildup on this side and a negative buildup over here. Well, because, if this is, -3, whatever, -3 coulombs on this side, because of this thing that's connecting them in the middle, right? What does the charge on this side have to be? +3, right? If there's a -3 on this side, there has to be a buildup of +3 charge on this side. And then that means that on the other side here, it's also a -3. All of these, right, are going to have the same charge. If this is +3 coulombs, this is -3 coulombs. That means this one also has to be +3 coulombs just because of the way these things are connected, right? If I take 3 electrons over here, I got an excess of 3 protons over here, right? So that's the way it works. And then, again, -3 charge on this end, and then blah, back to the beginning. So in series, all of the charges are the same on each thing. But another thing that we can notice is that the voltages must add up to 9 volts. The voltage drop across this one plus the voltage drop across this one has to add up to 9 volts, right? If I track it, right, 9 volts, 9 volts, 9 volts, 9 volts. There's 9 volts here on this positive end. If I track the negative terminal, 0, 0, 0, 0, 0, blah, 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 0 volts right here, right? So there's a voltage drop across both of these that have to sum up to 9 volts. They don't both necessarily have equal voltage drops across each one, but they must add up to a voltage drop of 9. And so the way we're going to treat this one is if I combine these into one equivalent capacitor, the total voltage across the whole thing has to be equal to the voltage drop across capacitor 1 plus the voltage drop across capacitor 2. Again, going back to the relationship C is equal to charge divided by voltage. The voltage, if I solve this for voltage, it's going to be charge divided by capacitance. So this equivalent, capacitor, it has 9 volts, right? And all of these are having the same charge, right? We already said everything has the same charge here. So this is going to be rewritten as charge divided by equivalent capacitance. And that has to be equal to the voltage across capacitor 1. That's its charge divided by capacitor 1. And the voltage across the second capacitor is its charge divided by its capacitance, C2. All of these charges are the same. We said in series, right? No matter how I set them up, they're all going to have the same charge on them. So I'm not differentiating between the charges here. It's all the same. I can cancel these out. So if I wanted to solve for the equivalent capacitance for a series configuration, I'm going to do these ratios of 1 over C1 plus 1 over C2. And if I have more than that, I will just keep adding them continually. So that's how we deal with the series configuration. Let's put them all together and see how we deal with stuff that has both series and parallel combinations. Let's say here's our battery, and maybe we have a capacitor here. And a capacitor here and a capacitor here. Again, we draw these we draw these circuit diagrams so nice and neat in the textbook. In real life, our circuits do not look this nice and pretty and neat. And let's just choose some values here. Let's say the battery, let's mix it up, 36 volts battery. And let's say that this capacitor right here is 4. And I'm going to say everything is in microfarads. And these two, let's say this one is 24 microfarads and this one is 8 microfarads. The question will be, what is the voltage drop across each of these capacitors and what is the charge on each of these capacitors? We should be able to do that. The key to working through these is you kind of have to put the puzzle together and then take it apart again. Okay, so what you're going to do is combine these 3 capacitors into one equivalent capacitor and then work backwards to figure out the voltage and charge on each thing. So let's do that. The first thing that we should combine here, just kind of by looking at it, is let's combine these two that are in series with each other. Notice that these are in series. So let's combine them into one equivalent capacitor, and then we'll deal with the whole thing. When they are in series with each other, we're going to use 1 over the equivalent capacitance is going to be 1 over 24 microfarads plus 1 over 8 microfarads. One over 6 microfarads. So one key, when you are doing these equivalent capacitance, especially for the one in series, don't forget to inverse. Do the inverse at the end. Sometimes people forget to do that. So I have to do the inverse here, take 1 over each side. The equivalent capacitance is going to be 1 over 1 over 6, so that becomes 6 microfarads. So I have combined these two in series to create one equivalent capacitor that is now 6 microfarads. Now these are two capacitors that are now, as you can see, in parallel with each other. So now these are parallel configuration. In the parallel configuration, we just add them. So this is going to be 10 microfarads. So we have taken this somewhat complicated circuit and reduced it down to one equivalent capacitor of 10 microfarads. All right, so now what do we do? If I'm trying to figure out the charge and the voltage across this 24 microfarad one, what do I do now? We have to work backwards. Okay, so I know that I have a 36-volt battery here and a 10 microfarad capacitor. Let's figure out the charge on this thing. This is connected to 36 volts, so the voltage across this is 36 volts. Its capacitance is 10 microfarads. I can now use the relationship between charge, capacitance, and voltage to find the to find the charge on this one. If you remember, capacitance is charge divided by voltage. So the charge on this one is going to be equal to its capacitance multiplied by the voltage. Capacitance is 10 microfarads. Let's convert that now into farads. A micro just means times 10 to the negative 6. So 10 times 10 to the negative 6th farads. Multiply that by 36 volts. 3.6 times 10 to the negative 4 coulombs on this one, on this equivalent capacitor. My email's going nuts right now, sorry. Okay, 3.6 times 10 to the negative 4 coulombs on this one. Let's now work backwards. Let's take a step back and look at this configuration. 36 volts, 4 microfarads, and 6 microfarads. They're in parallel with each other. If you remember, when they were in parallel with each other, they had the same voltage. So the 4 microfarad one has 36 volts, and the 6 microfarad one has 36 volts. Again, I can figure out the charge on each one of these by using this relationship. Q is equal to CV. So for the 4 microfarad one, the charge on it, sorry, I should have drawn this bigger. The charge on this one is going to be its capacitance multiplied by the voltage across it, which is 36 volts. So I'm going to do 4 microfarads, or 4 times 10 to the negative 6 farads, multiply that by 36 volts, 1.44 times 10 to the negative 4th coulombs. I'm do the same thing for the other capacitor. It has 36 volts across it. It's 6 microfarads. If I do 6 times 10 to the negative 6 farads multiplied by 36 volts, 2.16 times 10 to the negative 4th coulombs on that one. Notice, and these are actually really good problems because you can keep checking your work as you go. Notice that the charge on each of these adds up to the total charge that we would have had on this equivalent capacitor down here. 1.44 plus 2.16 is going to be 3.6 times 10 to the negative 4th coulombs. Okay, so let's go back. We're taking the puzzle apart again. Let's go back one more step. We already said the 4 microfarad one has 36 volts across it and 1.44 times 10 to the negative 4th coulombs. Now for the 6 microfarad capacitor, if we work backward, it turns into two capacitors in series with each other. If you remember, because they're in series with each other, they have the same charge. So both of these are going to have the same charge as the equivalent capacitor had, which is 2.16 times negative 4 coulombs. So I know their capacitance, I know their charge. The last thing I want to figure out is what is the voltage drop across each one of these. We can go back to the relationship between charge, voltage, and capacitance. The voltage is going to be the charge on it divided by the capacitance. So for the 24 microfarad one, I'm going to take 2.16 times 10 to the negative fourth and divide that by the capacitance, 24 times 10 to the negative 6 farads. 9 volts across this upper one. Can you make a prediction about what the voltage should be for the bottom one, the 8 microfarad one? If this upper one is 9 volts, make a prediction, and now let's calculate it. The voltage across this one is going to be its charge divided by its capacitance. So I'm going to do 2.16 times 10 to the negative fourth. Divide that by 8 microfarads, or 8 times 10 to the negative 6 farads, 27 volts. 27 plus 9. That looks familiar. 36 volts. That's the voltage of the battery. And that's, if I track this, right? This is 36 volts on this side. If I track the other side, negative terminal is 0. There should be a total of 36 volt drop across both of these. This is a 9 volt drop. This is a 27 volt drop. The total drop is 36 volts. It works. So the cool thing about these kinds of problems is you can always check your work. You can always make sure it's making sense as you go. But that's the way you kind of treat these problems when you have multiple capacitors in combinations of series and parallel. Work forward, get your equivalent capacitance, and then work backward. And just remember that when they're in series, they have the same charge. When they're in parallel, they have the same voltage.